Our function is odd positive and is x cubed plus 3x squared plus 0 and is a third degree function. This is our graph. You can tell that the y-intercept is 0, 0 by the equation, with the turning points of 0, 0 and 0, negative 3. The turning points are 0, 0 and negative 2, 4. You can find the zeros by using this Descartes' rule of signs discussed later in the video.
The basic factoring of polynomial equations.
There's the sum of two cubes represented by this equation, and the difference of two cubes represented by this equation. To factor by grouping, first you would separate the equation into two, then take out the greatest common factor. You then put together the x squared and the negative 2 into one side and x plus 5 in the other, and it is factored. To combine cubes and squares, you separate them into 2 by 3. You then take out the greatest common factor and put the greatest common factors together. And the x squared minus 3x plus 2 in the other one together. You then factor x squared minus 3x plus 2, and you use the sum of two cubes for y cubed and z cubed. And when you fully simplify it, and you combine the two to get your answer.
Like Ashley mentioned at the beginning of the video regarding the function, you often need to use Descartes' rule of signs in order to figure out the number of positive real zeros, negative real zeros, and imaginary zeros. Let p of x be a polynomial function with real coefficients. In order to find how many positive real zeros there are, you first need to take positive p of x and count how many sign changes there are, or how many sign changes minus an even number. This will make sense in a moment. In order to find negative real zeros, you do the same thing except for you're using p of negative x, which you'll again see is very important later on. You might get a problem where it asks for you to state the number of positive real zeros, negative real zeros, and imaginary zeros of a particular function, like this one. In order to find the number of positive real zeros, you're going to count the number of sign changes between each term. So in this function, there's only 2, which means you might have 2 real zeros, or you might have 0, because if you take 2 and subtract it by an even number, 2, then you get 0. In order to find p of negative x, or to find the number of negative real zeros, then you're going to plug in a negative x everywhere there's an x. Takes a little bit of time, but essentially your equation should look like this. Once you have that, you're going to reduce it down and figure out what you have left. So for example, on the first term, the negative x to the 6th power is positive, but it's being multiplied times a negative on the outside, so it remains negative x to the 6th power. You continue to do this throughout the entire equation in order to figure out your signs for the p of negative x function. Once you have the p of negative x function, count the number of sign changes just like you did for the positive one, and that will give you the number of negative real zeros. And last, in order to find the number of imaginary zeros, you first need to look at the number of total zeros. In this equation, it's 6 because the leading degree is 6. So you look at your positive and negative options, so it could be 2 or 0 in this case, and find out how many other zeros there are. So for the first row with 2 positive and 2 negative, if your total is 6, then the number of imaginary, or whatever's left over, has to be 2. Like Ashley was mentioning at the beginning of the video about polynomial factoring, another part of this is polynomial division. In order to divide a polynomial, you must use synthetic division. So for example, if you're given a problem where you have to divide two polynomials, you're going to draw a left corner box, a line underneath that, and then a little space for the remainder. So I know to put a 9 in the left corner box because you're essentially going to set the second equation, x minus 9, equal to 0. Then you're going to bring down the coefficients from the first equation, the x squared minus 10x plus 9. You're then going to bring down the first coefficient, which happens to be 1, and place it underneath the line. Then you're going to multiply the 1 times whatever is in the left corner box, in this case, positive 9. 1 times positive 9 is positive 9. You'll put the resulting answer underneath the negative 10. Then add those two together and continue this entire process until you finish and run out of numbers. So your answer is x minus 1 with no remainders. When working with polynomials, there are a few theorems you need to keep in mind. Abby will go over the remainder theorem and the factor theorem. If you notice, in both of the theorems, you're still using synthetic division. The idea of the theorem is to help you understand why you are solving the problem and what the answer means. Another important theorem of algebra is the fundamental theorem of algebra, which states that every polynomial equation with a degree greater than 0 has at least one root in the set of complex numbers. Now, the corollary to the fundamental theorem of algebra states a polynomial equation of a degree n with exactly n roots in the set of complex numbers, including repeating roots. So for example, if you have x to the third plus 2x squared plus 6, you know it has 3 roots because of the degree of the polynomial function. The fundamental theorem of algebra definitely comes into play when working with roots and zeros, which Isabella is showing us right now. She is setting the equation equal to 0 and then continuing to solve in order to find the roots for this polynomial equation.